Imagine you're trying to see a forest in exquisite detail, not just the shape of the trees, but their exact species, health, and even subtle changes due to drought or disease. That's the power of hyperspectral imaging. It captures how light reflects off surfaces across hundreds of narrow spectral bands, revealing material composition with incredible precision. But there's a trade-off. High spectral resolution means low spatial resolution. You might see the forest's chemical signature, but not individual trees. Now imagine combining that rich spectral data with a high-resolution multispectral image, one that captures sharp spatial details, but only a few broad spectral bands. If you could fuse these two, you get a high-resolution image with full spectral richness. This is called hyperspectral superresolution, and it's a cornerstone of modern remote sensing. But here's the catch. In real-world applications, these two images are rarely captured at the same time. One might be from a satellite passing over a region today, while the other was taken weeks or even years ago. And during that time, the scene changes, sunlight shifts, clouds pass, vegetation grows or dies, and even soil moisture fluctuates. These temporal changes introduce what researchers call interimage variability, differences in both spectrum and spatial structure between the hyperspectral and multispectral images. This variability breaks the assumptions of most fusion algorithms. Traditional methods assume that the spectral and spatial characteristics of the scene remain stable, but they don't. And when that assumption fails, the fusion results degrade: blurry edges, color distortions, and lost structural details. So how do we fix this? In this video, we dive into a groundbreaking new method called degradation-based low-rank and residual fusion, a model that doesn't just handle interimage variability, it models it from the ground up. Let's break it down. First, the core idea. Instead of treating spectral variability as a change in the image itself, which is messy and ill-posed, DLRRF models it as a change in the spectral degradation operator. Think of the spectral degradation operator as the fingerprint of how the sensor translates real-world reflectance into measured data. If the lighting or atmospheric conditions change between acquisitions, that fingerprint changes too. So instead of trying to correct the image, we model how the sensor's behavior has evolved. This is a subtle but profound shift. It moves the problem from image correction to system modeling, and it's far more robust. Next, we tackle spatially localized changes, like a tree falling, a new building appearing, or a field being plowed. These cause abrupt differences in the scene that can't be captured by smooth, global models. To handle this, DLRRF splits the target high-resolution hyperspectral image into two components. A low-rank component, which captures the global, smooth, stable structure of the scene, like the dominant vegetation or terrain. A residual component, which captures the fine-grained, localized changes, like the sudden appearance of a vehicle or a freshly cut field. By separating these two, the model can recover lost spatial details that traditional methods would smooth out or ignore. Now here's where things get mathematically elegant. Since hyperspectral images have strong spectral correlation, meaning neighboring bands are highly similar, we project both components into a lower-dimensional spectral subspace. This is done using truncated singular value decomposition, which extracts the most important spectral patterns. This dimensionality reduction dramatically reduces computational cost while preserving essential information. But here's the real innovation: implicit regularization via the plug-and-play framework. Most models rely on handcrafted priors, rules like images should be smooth or spatial patches should be similar. But under interimage variability, these priors break down. They're too rigid. Instead, DLRRF uses an external denoiser, like BM4D or a deep neural network, as a plug-in prior. This denoiser implicitly learns spatial structure from the data itself, without requiring us to define a mathematical function. It's like giving the algorithm a common sense about what a real image should look like, even when the scene has changed. The whole model is optimized using the proximal alternating optimization algorithm, which alternately updates the low-rank component, the residual, and the spectral degradation deviation. And critically, the authors prove that this algorithm converges to a critical point, not just empirically, but theoretically, using the Kurdyka Łojasiewicz property, a powerful tool in non-convex optimization. Now let's talk results. The researchers tested DLRRF on 4 real-world datasets: Lake Isabella, Lake Tahoe A and B, and Ivampa Playa, all with significant time gaps between HSI and MSI acquisitions. They compared against 5 classic fusion methods: GLPHS, CNMF, High-Shore Stereo Scott, and 3 advanced methods specifically designed for interimage variability: foo-var, CB-star, and BTD-var. The results: DLRRF consistently outperformed all competitors across multiple metrics: PSNR, SSIM, ERGAS, SAM, RMSE, and UIQI. On the Lake Tahoe dataset with a 3-year gap and a 4 times downsampling factor, DLRRF achieved a PSNR of 25.61, beating the second-best method by over 1.5 dB, a massive improvement in image quality. Visual comparisons show it. While other methods produce blurry, color-shifted, or artifact-ridden images, DLRRF reconstructs both visible and infrared bands with remarkable fidelity, matching the ground truth in tone, structure, and fine detail. Even more telling, ablation studies prove that each component matters. Removing the spectral deviation term drops performance. Removing the residual component hurts spatial detail recovery. And removing the implicit regularizer degrades the spatial coherence, proving that every piece is essential. And here's a killer application: classification accuracy. When fused images were used to classify land cover using an SVMKC classifier, DLRRF boosted overall accuracy by 16.8% over the original HSI and 4.2% over the MSI. A clear signal that better fusion leads to better real-world decisions. In terms of speed, DLRRF strikes a balance, slower than the ultra-fast BTD VAR, but significantly faster than FU VAR and CB star, while delivering far superior results. So what's the takeaway? DLRRF isn't just another fusion method. It's a paradigm shift in how we think about hyperspectral superresolution. By modeling spectral variability as a change in the degradation operator, decomposing the scene into low-rank and residual components, and using implicit priors through PNP, it tackles the root causes of failure in real-world data. It's robust, it's theoretically sound, and it delivers state-of-the-art performance, even when images are captured under drastically different conditions. This is the future of remote sensing, not just fusing images, but understanding the physical and temporal dynamics that shape them. If you're working in AI, remote sensing, or image reconstruction, this paper is a must-read. And if you found this breakdown helpful, consider supporting the channel. We're here to bring the latest research to life, one deep dive at a time. Thanks for watching. Stay curious.